Okay, good morning, everybody. All right, now, okay, so let me do a few things here. Let's remind you guys of a few items. Let's go to the browser and say, okay, here we go, our browser. And we're going to go to Math 262. And yes, our online transition. And just reminding you guys here, we have some series and we have some good examples here. Um, I want to make sure you guys, we do have 19 views, which are good, and make sure that you guys take a look at these again because we have, some very good examples of things that you could possibly see for geometric series here. So make sure you get to see that. And again, I might put some of the integral test examples too. We'll see about that one. Anyway, today what we're going to look at is going to be the comparison test. And we're working with series, and remember, we want to know whether a particular series actually converge. And we have a new test. We're going to look at various tests. And we want to look at today the comparison test. Now, the comparison test essentially is about comparing. And so we're going to have to assume here, we're going to say that suppose we have two series, some AN and some BN. And then they have positive terms. And this is an important detail. Now, to say that they have positive terms here, here's really what this means. It means that AN is greater than 0 and BN is greater than 0, and we say this for all n. So they're referring to the terms of your series here and here. They want those to be strictly positive. And that's the assumption here. And so what we'll do now here is, and give you the test so you guys know how this works. And it's going to be two cases. One, if AN is less than or equal to BN for all n, and we need to know something else. We need to know that the series, the bigger series here. Okay, so remember this. We're going to say AN is actually going to be convergent. This means converges, right? And or the sum is finite, some value. And you're going to see what we mean by the bigger series. Okay, because if we have this assumption here that AN is less than or equal to BN, what that means is if we add the terms AN and we add these terms together here, this is also true. This implies that, if for every term AN is less than or equal to BN, then the sum of AN is less than or equal to the sum of BN. And so what I started to use the phrase, the larger, right? Larger series here. I use that phrase, larger series. So they're saying with the assumption, if really the larger series converges, then we know the smaller series will converge. So this is going to be the conclusion here. This is in comparison, right? Then so the smaller series, AN, is also finite in its sum. So this also converges. And that's really a sort of logical comparison that we're going to look at. And so if you might say, well, is there an example of something like this? right? So yeah, there is an example. I want you guys to recall this series here that we looked at, 1 over 2 to the n. This equals 1. This is a geometric series that we looked at, and it converges. Now, that's not the example, but if they said to you, what about 1 over 2n plus 1? You know, and really, there's nothing special about 2n plus 1. They can give you something very similar, like 1 over maybe 2n plus 20. Doesn't really matter. What about convergence for a series that looks like this? A series that looks very similar. And that's actually going to be something that's going to be key for us as well in our future. You'll see what I'm talking about. This series here that we just gave you with this first example is very similar to the one you guys see here. They're very similar. And that's going to be a key thing. Anyway, here's what we know. That there's a relationship here between the two series, right? Let's write this down. What's the relationship? Well, we're going to relate 1 over 2n plus 1, we know is smaller than 1 over 2n. Now, you say, how do we know that this is actually smaller? Well, because look at the denominator here, right? 2n plus 1 is actually bigger than 2n for all n. You see, what we know is this thing is actually bigger than this for all n. And there's a piece of logic that that we can look at, and I can say to you, if for positive numbers, right? If A is positive, B is positive, and you have maybe A bigger than B, then we can prove that the reciprocal 1 over B versus 1 over A, it actually flips direction. This is a point. I mean, I guess I could do it this way. I can say 1 over A versus 1 over B, and it's going to be pointing to this 1 over A. So, I mean, I can prove that, but the point I'm making is we can transition from here to over here, and, this just simply the direction flips with your inequality, okay? So I can actually prove that statement, and what we know is this relationship is actually true. And it kind of makes sense because if you make this denominator bigger, than what it was, the fraction is smaller. And that's kind of what's happening there. So anyway, what we know here is that 1 over 2n plus 1 will be smaller than 1 over 2n by comparison. And we also know that the bigger series, this series here, the bigger series, is finite. So that forces this whole thing, the smaller, and I wanted to change colors, it forces the smaller series to also be finite by this inequality. Okay, so that forces, by comparison, that the smaller series in this example, we can say also converges. And that's the essence of the comparison test. Now, there's nothing special about, 2n plus 1. The same rule applies to 2n plus 20 or 2n plus 2, 2n plus 3, whatever. If you add a value, you just simply make it bigger. So this is what we're saying here. And again, yes, all the terms must be positive for this to be valid. All the terms have to be positive for both series. And this is the comparison we start with. This is the comparison of the series. And so the larger series converges implies that the smaller series, this one was smaller. And that smaller series converges. Now, that's by what we say comparison. The second thing that we have to say by comparison in the comparison test is we have another criteria. If AN is at least as big as BN. For every term. And how did I write that? I put it down here. Oh, yeah, we did. Okay, I'm going to do it the same way. And this time, ladies and gentlemen, we have the following relationship. AN, this means diverges. Remember, symbolically, this is what we're saying. This diverges. This is why that notation was good. So this series diverges. And what we're going to compare again is we're going to look at this and say, okay, sum AN is greater than or equal to sum BN. Now, this is written a bit backwards, but I want you to know something like this. This is what this means. This is actually larger, right? And this is smaller. And so here's what's happening. Since the larger series, and I put this equal to infinity, since the larger series diverges, right, all those terms add up so big that it's uncountable. You know, it's not a million, it's not a billion, it's not a gazillion, it's not a trillion. It's not one. It's not finite. They add up and they're big, right? They're so big, they're uncountable. Well, if the larger series diverges, and here's my larger series. If the larger series diverges, this forces then we say the smaller series also must diverge. And this is really what they're saying. Okay, so this is by comparison. So let's wrap our head around that, right? So we're saying that, wait a minute, if a smaller series diverges, then the larger series must diverge. Because the sum is going to be bigger, right? So in any way, this here, let's double check the notes. Let me write it exactly the way your book does, because I don't want to confuse you guys and keep it the way the book is. So let me double check here. Did the book do it that way? You say AN, BN, and BN is convergent. Yes, we're good with what the book says there. Okay, then AN is convergent. Okay, now let me be careful with this book. I might have to. So your book says that if AN is greater than BN for all n, yeah. And we made a mistake here. That's right. There it is. That's what something was really wrong. Where's Marbella when we need her? Is she here? Hey, Marbella, we need you. If BN, I apologize here. Yeah, BN here is divergent. So let's double check. AN, BN for all n. Then AN is, there we go. That was bothering me here. So let's make sure everything else is okay. So let's double check here. This is the larger series, right? This is larger. This is smaller. All right, we got it out here. There we go. Larger series. Okay, smaller series. Oh, there we go. Yeah, now that makes more sense to you guys here. So here's what's happening here. We got to erase this. This is the deal. The smaller series, ladies and gentlemen, now that makes a lot more sense. The smaller series diverges. So if the smaller series has a sum that's infinite over here, here's the smaller series. And that's the assumption. The smaller series sum explodes, then there is no way that the larger series can have a sum that's finite. So if the sum there of something smaller in comparison is actually infinity, then the larger series, it's forced the larger series to be divergent as well. There we go. And that's kind of how I remember it. Smaller series diverges, then the larger series diverges. Okay, so you can write that down as well. Over here, if the larger series converges, then the smaller series converges. And I could show you another example of this divergence. And, it's kind of a typical example, but let's go through something like this. Let's show you an example of this now. They can say to you, what if you have this series here? 2 over, I could make this a little bit different. I can say, how about 3n cubed plus 2n minus plus 6 here? Okay, make sure we could always have positive terms. 1 to infinity. Actually, this is going to be a convergent series. I don't want to give you that one. So I'll give you the one that our book has as a quick example. 1 to infinity, natural log of n over n. And so here's what they want you to consider, right? The natural log of n is actually bigger than 1 for all n. And I think for n greater than what? If n is, remember, n is going to be what? 1. And natural log 1 is 0. N is 2. So let's take a look at this here. Let's take a real quick look so we can see what's going on with this natural log curve. And here we are at 1, 0. Right? Natural log curve really looks like this, but we're looking at these points here. 0, 1, and so on. All right, so let's create the right inequality here. And here's this here isn't true for all n. So here we're going to say n is going to be 1, 2, 3. And so we have to know, I believe, starting at 3. So here's what's really happening. This isn't true for all n. This is true starting at n equals 3. Okay, so I believe it's about 3. So we're going to have to know what the natural log of 3 is and see when that starts to be bigger than 1, because a natural log 1 is actually 0, and natural log 2, we'll see what that becomes, but we need natural log of 3 here. So let's get this out for you guys. Okay, let me get my trusty, natural log 3, ladies and gentlemen, so you guys know, is approximately 1.0986. So starting at 3. Anyway, this is going to be okay because it's not about where it starts, it's about where it ends. So we need n to be greater than or equal to 3. So anyway, you say, okay, I have that. So we know the natural log of n is bigger than 1. And, we could divide both sides now by n. Is that true? And it doesn't change our inequality. So what we know here is that the sum then of natural log n over n is going to be bigger than the sum of 1 over n. So as you guys can see here, the smaller series is the very famous divergent harmonic series. This diverges. This is equal to infinity. So if the smaller series diverges, there is no way that the larger series can add its terms and be finite. So this actually is a demonstration of showing you that this particular series, the natural log n over n, is also infinite. This diverges. Anyway, okay, so we got that little correction there, and here's the typical examples. Now, what we're really going to use, if you guys want to know the truth, we're going to use something called the limit comparison test. But the limit comparison test starts by thinking of the comparison test. So for the limit comparison test, I'm going to write that down for you, because we're going to prove it as well. For the limit comparison test, here's what this is. It starts with the same assumptions that you suppose or assume we have two series, some AN and some BN are series with positive terms. Okay, so we talked about that. This is what they're talking about. These are the two series. The terms are positive, meaning AN is greater than 0 and BN is greater than 0 for all n. Okay. And then they're going to also say you're going to let C be a constant. Well, it's going to be a constant, and we're going to talk about that value C. So here's the limit comparison test. If the limit of the ratio AN over BN is equal to some constant C, where this is the criteria on C, the constant. First of all, they're talking it's finite. It's a finite value. And C must be positive. If you have this, then we can say the following. Then either both series converge or both series diverge. And this is the limit comparison test. This is the big assumption. This is really where all your work is going to be, right in here. Okay, so you're going to look at the ratio of these, and you're going to find if that limit, and this is an if-then statement. It doesn't go both ways, right? It's if the limit of the ratio is a constant, it's a finite value that's positive, then either both series converge or both series diverge. Now, like I said, I'm going to give you guys the proof to this. So here's the proof of this, and it starts by simply saying, let little m and big M be positive integers. I actually prefer, personally, saying natural numbers, because that makes them positive integers, right? Natural numbers. Anyway, and we're saying let these values be natural numbers such that this relationship is true, that little m is smaller than C, which is big M, that constant C we're talking about, okay? Now, this is starting the proof. Remember, you say, what's the assumption here? Right here is what we're going to assume. It's an if-then statement, right? A conditional. It's if P then Q. So this is our assumption. We're assuming that the limit of the ratio is C, where C is finite and positive. And so let's recall that we are assuming that that limit of the ratio equals C. And yeah, C is positive. And that makes sense because M and M, the M's are actually natural numbers, are positive integers. So this is where we start our assumption. Now, by that assumption, what this means is that AN over BN are quote unquote close to C because it's a limit. And they're close to C for large N, meaning eventually, right? For some terms, it's a limit. That ratio goes to C. So for large N, this ratio is close to C. And that's what they're saying. And what that really means, for large enough N, we have that particular relationship, that M is less than that ratio, AN over BN over M, and that's going to happen for, for some, we write that natural number N, really. I mean, eventually is what they're saying, because we have this convergence. So all they're saying is, okay, we're replacing this C value with that ratio. And that happens eventually for some natural numbers N. And it's just for some terms, eventually it's going to be within that interval. Now, since we have positive terms again, we just use some algebra, meaning we get to multiply Bn, the bottom series here, to all three terms. And you say, well, what does that give you? Well, it gives you M, Bn less than An less than big M, Bn. We multiply. Just using some algebra. And that happens again for we'll say some natural number bigger than N eventually, so it'll be formal. And now take a look at what this is. This is going to be the key. If Bn is finite. Okay, so we're going to take the Bn series, and remember, that's what we know. If Bn is finite, that's this assumption, that sum, if it converges, then what that means is that the sum of MBn, since m's a positive constant, by properties of series, bring out that MBn, that's also finite. So notice the genius of this. I'm going to look at the sum here of that relationship and do a little bit of algebra. Bring out that little m, sum Bn, sum An, and then bring out this constant m here. Give you every detail. And all they're saying here is assume here that this term is finite. And you say, oh, that's finite. Well, what does that mean? That forces, ladies and gentlemen, right in here. The smaller series must be finite. So if the sum of Bn is finite, then we know the sum of An is finite. And that's a big deal. So we have here convergence, and we have here convergence. And that's why they say in the limit comparison test that either both series converge. These series up here, An and Bn. So with that assumption, both series will converge. Now, you go back to that same inequality, and they're going to say now, well, if the sum here of Bn happens to be divergent, equals infinity. Well, remember, we're using this relationship here that came from this relationship. So we went from here to here. And then you say, okay, I know that this term here is actually going to be divergent. The sum explodes. Well, guess what? By properties here, that means sum Bn, I can factor out, I could pull out the constant m, sorry, not factor. And then I have m, which is a positive number, right, times this. This is infinity. So that's going to give me infinity. And more importantly, if I use this comparison, what we're saying here now is this is infinite. So the smaller series in relation to over here, sum an, the smaller series diverges, that forces, then the larger series, sum an, also diverges. And this is what you're looking at right in here. So the smaller series diverges, forces the larger series to diverge. And that is really the conclusion of the proof. Okay, well, I don't want to do that. It's right here. And that, again, means they both diverge. Okay? So they both diverge. So this is the conclusion. And this is why in the theorem it says both series diverge as well. So if we have that limit of the ratio is equal to C, and C is finite and positive, then we know both series converge and both series diverge. Now, it kind of seems at first glance that this is a bit not helpful, but it's very helpful, okay? Because here's what you're really going to do. I'm going to say go back to the original kind of question that we looked at, right? You say, okay, 1 over 2n plus 1. We already looked at the comparison test on this one. How do we use the limit comparison here? Okay, so this is kind of what they're going to give you here. So the big question is going to be, how can we use the limit comparison test? Right? Because I'm giving you these tests, we're talking about them, where they come from, because that's important to know. You're going to apply the test, right? So how do we start to use those things is the real issue. Now, whenever you're working with the limit comparison test, I'm going to say a phrase for you guys here. This phrase here is behaves like. Okay? And so here's what I'm going to say to you. The original series they gave me behaves like 1 over 2 to the n. And that is going to be something that, I got to double check to see if your book, I know I do it. It's been years since I've looked that over, but I say that behaves like, and it's very simple. You see, if you go back to the original series here, right? This is the original series that they gave us. If you remove some constant terms, meaning I'm going to remove now, this is a constant, this plus 1, I'm going to remove that constant term. If I start to remove the constant terms, I get a series that's very similar, behaves like it. And so this is our strategy. Get a series that behaves like it. I mean, the limit comparison just only requires, if you actually read that, two series that have positive terms. And if you look at the ratio and it equals C, which is finite and positive, then you know what? I mean, if it converges, well, then you can say something about this. But we want to look at something that it behaves like. And more importantly, it behaves like something we know. You say, what do you mean something we know? We know that this series converges. And you say to me, well, how do you know it converges? This was a geometric series. So go back, and the reason I said to you guys, go back and look at that series video that I gave a bunch of examples. That's gold. That's going to save your life, ladies and gentlemen. I recommend you watch it every night before you go to bed. Okay, because this is going to be, it's foundational. So the two examples I uploaded for you guys are very foundational for your sequence and series careers. So we know this one converges because it's a geometric series. We showed this already. Now let's look at how this limit comparison test really pans out. So here's what I'm going to say to you guys. We're going to call this here AN, and this will be your BN, because I need to look at the limit of the ratio AN over BN, and that's going to be the limit now of, you say, what was AN? Oh, 1 over 2n plus 1. And what was BN? Oh, 1 over 2 to the nth power. And you use, ladies and gentlemen, some algebra here. This is division. And when I divide here, I get the limit of 2 over n over 2n plus 1, and this is as n gets big. Okay. Now, you may have never looked at a limit like this. We're gonna start to look at these kind of limits. This is analogous to Calculus 1 limits, where you said, oh, don't I have to divide by the largest, or I should say, the variable with the highest power in the denominator? Don't I have to do that with every term? And I'm going to say to you guys, yeah, but what you see here is not what you've had in the past, but we're going to use the same approach. We're going to divide every term by that 2 to the nth power. So it's going to be analogous to what you did before, 2 to the nth power. So we're going to divide that by 2 to the n, 2 to the n. And what this gives us here is going to be the limit of 1 over 1 plus 1 over 2 to the n. Now, by properties of limits, if I go every detail, 1 plus that limit, 1 over 2 to the n gets big, and then, ladies and gentlemen, this portion goes to 0. So this is 1 over 1 plus 0, or better known as 1. Now, you say, okay, why is that a big deal? Well, that limit is 1. This is the constant c. This is finite. This is that c in the limit comparison test. And so the knowledge of us comparing to a convergent geometric series now says, guess what? This also converges. But we already knew that because we actually compared it. And that's an example of the limit comparison test, ladies and gentlemen. Anyway, pretty good. So knowledge of these things is going to be important for us. Let's see, something like, let's go here if I can recall. Yeah, let's recall that divergent situation here. Let's see if we could do something. Maybe that's a good idea. Maybe that's not. AN over 1 over n. Anyway, maybe we should just look at some more examples. We're going to look at some examples here. Okay. So this is the limit comparison test. You guys are going to use that. Let's start with another example. And they're going to say, okay, here you go. Now they're going to say, let's give you n cubed over n to the 4th minus 1. And they're going to start at 2. And you're going to say, Mr. Judge, why do they start at 2? Well, I guess they can't start at 1 because 1 minus 1 is 0. And yeah, you can start really anywhere you want. Okay, you can start at 2, you can start anywhere. Now, I'm going to say to you something. Remember, this series, BL, I use BL for behaves like. This series behaves like the following series. Remember what we did in the last example. All you want to do is start to get rid of the constant terms. Okay, because those terms, I know n is changing value. It's a variable, 2, 3, 4, and so on. But if you get rid of the constant terms, it's very similar. And that will give us n cubed over n to the 4th. And so if you use a little algebra, you go, oh, is that 1 over n? Yes. And what do we know about this? This is the very famous divergent harmonic series. Okay, so now we're going to use a limit comparison test. So an, and you say this is going to be my bn. So, okay, so the limit now of the ratio an over bn becomes n cubed over n to the 4th minus 1 over 1 over n. Oops. Forgot the phrase limit. Very important. Don't do it that way. N cubed over n to the 4th minus 1 over 1 over n. And this gives me the limit now of n cubed over n to the 4th minus 1 times n, which will be the limit now, n to the 4th over n to the 4th minus 1. And then, ladies and gentlemen, we're now in a calculus 1 situation. You divide every term by the variable with the highest power in the denominator. So this is n to the 4th over n to the 4th over n to the 4th over n to the 4th minus 1 over n to the 4th. And so this is my limit here of 1 over 1 minus 1 over n to the 4th. And ladies and gentlemen, you get 1 again. And this is that constant. This is c. And it's going to be positive, but the point is it's finite. And so what you know is that we compared it to a divergent series. This diverges. That means the original series that they gave us here also diverges. And formally, we could simply say it this way. This diverges by the limit comparison test. And so what I just have to do now, ladies and gentlemen, is show you some examples of this limit comparison test and have you practice. Right? So here's another one. And I'm going to make a remark after I finish this one here. Here's something that's similar. They want to know whether this converges or diverges. So use the strategy we talked about. We're going to start to remove the constant terms. So this behaves like the series. If I say, okay, I'm going to remove that constant term, I get n over n squared, square root of n. Now do some algebra. 1 over n, square root of n. 1 over n times n to the 1/2. And then, ladies and gentlemen, that's 1 over n to the 3/2. So this is what this behaves like. It behaves like that's a p series. And in fact, it's not just a p series. This is and here's how I start to write it personally. This is going to be a convergent p series. Okay, convergent p-series. All right. Now, we have a question here. Why does it diverge if it approaches 1? Thank you, Marbella. Because we're applying here the limit comparison test. And by the limit comparison test, if that limit here, if we go back to the theorem, if that limit here, right here, this is the key. If it's finite, if the limit of the ratio is finite, it's going to be positive, then either both series converge or both series diverge. And so we showed here that the limit is 1, which is finite. And so that means, oops, wrong one. I think it's the same answer. Yeah, we showed here the limit is 1. That means both series diverge because we compared it to, this behaved like a divergent, or not a divergent. It's called the harmonic series, which we know diverges. That means both of these series will diverge. And that's how that limit comparison test works. So essentially the short answer is, limit comparison test. This one here, though, take a look. If n is 3 halves, remember what we seen, I guess, yesterday, right? P is bigger than 1. When P is bigger than 1, we have a convergent P series. Now, this is why some of this stuff is important. Don't look at this the night before. I have students of mine that do very well with this chapter, sequence and series, and it's a notorious chapter. But you have to keep up with this, meaning make sure you see all the videos I post. Don't wait till the night before a test, right? Make sure you are keeping up with those extra examples because you get a lot of good detail there. And if you do, you're going to do well with this. If you don't, then you're not. So make sure you guys keep up with that because that's why I put it up. This is a convergent P series that we seen yesterday. So what you would do, ladies and gentlemen, is do the algebra, meaning this is going to be now called AN, and this is now BN. And you'd have to try to apply the limit comparison test here, or just even, some of these we know just by the comparison test that this series is actually well, let's try to apply the limit comparison test, see what happens. I can compare it and show you that, what's going to happen here. Yeah, let's try to do that. We'll try to use the limit comparison test since that's what we're looking for. So the limit of the ratio, AN over BN, is the limit of, and you say, okay, is AN n minus 1 over n squared, square root of n, and we're divided by 1 over n to the 3 halves. So I'm just going to say to you guys, if you guys notice here, this portion is really, I think that's n to the 5 halves, right? So we get the limit now, n minus 1 over n to the 5 halves times n to the 3 halves. Okay? And doing the algebra, looks like we're going to get some cancellation here, right? So what do we get? 3 halves here minus 5 halves is minus 2 halves, which is 1. So this is n minus 1. Double check that my algebra is okay. Double check that that's going to be just n, because I'm looking right here. Okay, so double check. Let's see I'm okay. Limit as n goes to infinity, 1 minus 1 over n, and then that limit equals 1 again. Now remember, what do you need for the limit comparison test? You need this value c has to be finite and positive. So this is the c they're talking about in the limit comparison test. So because we know we compared it to a series that behaves like, oh, it's a convergent P series, that means this converges as well. They both converge. And that's the limit comparison test. So you're comparing it to a known series, known convergence or divergence. And that's what's going to happen to you. What's going to happen is when you compare these questions here, you're going to see that knowledge of the geometric series, knowledge of a p-series, the harmonic series, the things that you know converge are going to pop up and diverge. And let's give you guys another example here of what I'm talking about. So this is based on past knowledge. So they're going to give you 6 to the n, 5 to the n minus 1, n is 1 to infinity. We want to know if this converges or diverges. Again, we're going to say this series behaves like, in comparison, right? Remove what? Start to remove the constant terms. And so when we do that, we get 6 to the n over 5 to the n. And this, ladies and gentlemen, is 6 over 5 to the nth power. Now, I'm going to ask you, what do you know about this series? Right? What do we know about this? This series diverges. And you say to me, well, why does it diverge? How do we know that it diverges? This series diverges because it's a geometric series where r is 6 over 5. And the absolute value of r, the absolute value of 6 over 5, which is 6 over 5, is bigger than 1. If you guys remember, when r is bigger than 1, we get divergence. So we know already this is a divergent series. This is the behave-like series. Now, to answer the question, here's the AN, that's the question. Here's the BN. We're going to use the limit comparison test. So by the limit comparison, we take the limit of the ratio AN over BN, which is the limit of, and again, it's going to be some algebra. AN is 6 over n over 5 to the n minus 1, and this is 6 to the n over 5 to the n, which will be the limit of 6 over n, 5n minus 1 times, remember, you multiply by the reciprocal, 5 over n over 6 to the n. Okay, and then I'm going to say something to you guys here. Let's see what we do here with this. You say, what's this limit? Well, let me try this out. I believe that's going to be, is that 30 to the n over 30 to the n minus 6 to the n? Double check, ladies and gentlemen. Because I just distributed, right? I multiplied my exponentials and I distributed down here. So double check my arithmetic. And then you're going to say, Mr. Judge, what do you do with this? We've never seen this before. I'm going to say again, it's similar to the question I did earlier. If this was calculus 1, we say divide every term by the variable with the highest power. Well, in this course, you see kind of the reverse. That's a constant to a power. You're going to divide every term by that 30 over n. So this will be the limit of that 30 over n divided by that term. You say, do I have 30 over n minus 6 over n and you're going to get the following here. You're going to get the limit of 1 over 1 minus, and then you say, what is this term? Well, this will be 60 over 30 to the nth power. And you guys know 60 over 30 is 1/5. So that's the limit of 1 over 1 minus 1/5 to the n. And that's a 5. Let's make a better 5. Okay. By properties of limits, 1 over 1 minus the limit here of 1/5 to the nth power, And you guys know that this portion goes to 0. And so you end up with here 1 over 1 minus 0, or just 1 again. So there's your finite value. There's your constant. Okay? That's the finite value c. So you say, why is that important? That's 1. Okay, if it's a constant, what do we know? Since this series is a geometric that we compared it to, it's a divergent geometric series, this means that the original series diverges. All right, you guys? Now remember, these are the details that you get with the extra examples that I show you guys. Remember, keep up with that, and if you do, this section is going to be a breeze, and then your final is going to be a breeze too, you know, because it'll be on your final. Anyway, here's an example. Let me give you another one, another interesting example here. This one's going to really make you guys think a bit. You know, oh my God, they're going to give me this now. Sum 2k minus 1 times k squared minus 1. Everything over k plus 1. K squared. Is it k squared? Yeah, k squared plus 4 squared. Anyway, yikes. Just want to double check to see if we're okay with this. And you know, it's a good question. We got some time. Let's try to get that in. Limit comparison test, right? So remember, this series behaves like. What will it behave like? Let's start to think about this. I'm going to start to remove the constant terms. Okay, you see all these constant terms? I'm going to remove them. And when I do, what do I get? I get this 2k times k squared over k times, and it's going to be k to the 4th power, remember? Because if this is gone, the 4 is gone, 2 squared is 4. And you say, okay, what is this going to be? Well, this is sum 2k cubed over k to the 5th. You say, what's this? Well, that's 2 sum 1 over k squared. And you might say, what is this? Let's focus. This is going to be a convergent p-series. So I'm going to use this series to compare it to. Okay. Or I can say I can use this series here. 2 over k squared. Anyway. Convergent p-series. This is going to be some algebra. Here's an. Here's my bn. We're going to keep that kind of simple. So by the limit comparison test, I say, okay, what's the limit here? Limit of an 2k minus 1 times k squared minus 1, everything over k plus 1, k squared plus 4 squared, divided by 1 over k squared. Don't forget, this really is going to be multiplying by the reciprocal. 2k minus 1, k squared minus 1. k plus 1. And then I'm going to have here k squared plus 4 squared times k squared. Now, I don't know about you guys. I think I just noticed something here. I'm going to simplify a bit. Okay, there's no, isn't that k plus 1, k minus 1? So here's what I'm saying. I'm going to cancel the k plus 1s out. I want to simplify my life. So we have limit 2k minus 1, k minus 1 over k squared plus 4 squared. And this is times k squared. Okay, so go through the algebra. What is that going to give me if I go through some algebra? I mean, I can kind of fake the algebra a bit. I kind of know the answer, but let's go through it. Okay, 2k squared outer term minus 2k inner term minus k plus 1. Let's go through this algebra here. And on the bottom, you guys know you're going to get k to the 4th plus 4k squared plus a 4k squared plus a 16 down there. And you're going to get this limit. It's going to be 2k to the 4th, right? Minus, let's simplify before we distribute. 2k squared minus 3k plus 1. And that's going to be times k squared over k to the 4th plus 8k squared plus that 16. You're going to get the limit of 2k to the 4th minus 3k cubed plus k squared over k to the 4th plus 8k squared plus 16. Now, and this is k goes to infinity because they gave us a variable k. Now, what you guys would do is use calculus. Divide by the variable with the highest power in the denominator. And what you'll see, ladies and gentlemen, when you do that, you'll get the limit of 2 minus 3 over k plus 1 over k squared, I believe, over 1 plus 8 over k squared plus 16 over k to the 4th. Double check, something like that. Anyway, the point I'm making is this limit's going to be equal to 2. Okay? And more importantly, this is finite. And that's the point. You want this limit to be finite. And what does that mean if it's finite? That both series converge or both series diverge. And oh, here we go. Now, what do we know? This is a convergent P series that we're looking at. That means this series also converges. And it converges by the limit. Here's what limit comparison test, if you want to abbreviate it. So sometimes people abbreviate it. Sometimes I abbreviate it. Like I abbreviate behaves like here for you. Converges by limit comparison test. And this is how we start working with the limit comparison test. So I definitely want to do this. I want to give you guys some more examples. I do have some more examples to give you. So I'm definitely going to, since today is Thursday, what I'm going to do for you guys is a couple of things here. I'm definitely going to give you some more examples like on the limit comparison test. And I would recommend to you, some of you guys are going to look at the comparison test and you're going to compare, you're going to try to compare everything. And I would say that's not a good idea. Like we started the lecture talking about comparison and I showed you how to compare two situations, one that's convergence and one that's divergence, just by the comparison test. And the real thing we want to show you is that from the comparison test, you get what's called the limit comparison test. And that's what we really want to use. So start to use here. This is what I'm saying. Start to use the limit comparison test, ladies and gentlemen. And it's very specific. The terms have to be positive. So be careful. Every term for both of these series needs to be strictly positive. If they are, you could use this limit comparison test. They're going to give you questions that are doable. Meaning when you start to remove those constant terms and it behaves like, and I'll give you some more examples with this, hopefully by tomorrow at least, right? Give you more limit comparison. But as you guys can see, if you don't know about a geometric series converging, or if you don't know about a p-series converging, or you don't know about the harmonic series being divergent, then you're not going to be able to conclude or even use the limit comparison test, because it's based on your past knowledge of what converges and what diverges. And that's the key. So there's some very famous series here, and it's going to be, so far you guys have like the p-series. You're going to show that it's going to be comparable to a p-series, comparable to a harmonic series, comparable to a geometric series. So make sure you guys look at those videos that I upload for you guys. And if you are subscribers, and I think you are, you actually get notification by YouTube when it goes up. So what I'm going to do this weekend for you guys is, as well, get you some more limit comparison test examples. I might even give you a very quick alternating series, the test for alternating series. It's very simple. So I might do that. We'll see how it goes. I don't know. But yeah, I'll get you guys some more examples. Make sure, though, because your final is going to creep up on you, and sometimes some students, they wait till the last second and then they cram everything, and I'm going to tell you, it never works out. It's never worked out for me. It's never worked out in my whole career of working with students for over 20 years. If it could be done that way, I would do it. But anyway, 12.4 here is the section. So I'm going to say work on like 3 to 31 odd. I'd even say do them all. And I might give you some more to do and prove some more this weekend. We'll see how this weekend goes for me. But anyway, nice, good stuff. Limit comparison test. Yeah, and then you might want to start to read 12.5. The alternating series test. I don't know. We'll see. Alternating series tests. Yeah, I mean, well, we might even do that Monday. We'll see. I might leave that till Monday. Yeah. So you can read that if you wanted, but start and try to get up to 12.4 this weekend if you can. All right. And if you have any questions or issues, see me during office hours. I'll send you guys a link, Zoom link for office hours, so that I can merge both classes together, and make sure you get that. You'll get that in Canvas. So have a great weekend. I hope you guys stay safe, study hard, and stay inside and just focus on your calculus. All right. So take care.